Hello all, and welcome to another installment of the University of Alberta Geotechnical Graduate Student Seminar. Only one brief announcement today. The APEGA Student Liaison Committee is hosting an event tonight called Marketing Yourself a Good Hire Series, a geoscience mixer. This event will allow you to network with a variety of geoscientists working in mining, oil and gas, hydrogeology, and other related disciplines. Along with your peers, you will have the opportunity to have meaningful interactions and discussions with industry professionals, expand your knowledge of the different industries within geoscience, and learn about different tricks of the trade. I'll post a link to the sign up in the chat box. So now diving into our presentation. Today we have a presentation from Gabriella Wahl. Gabriella completed her bachelor's degree in civil and environmental engineering from the U of A in 2018 and is now working towards her MSc in geoenvironmental engineering under the supervision of Dr. Ward Wilson. Gabriella is an active member of the U of A community, helping to plan events through serving as an executive board member of the UACGS student chapter. Today, Gabriella will be speaking on her current research about acid rock drainage at Faro Mine. Acid rock drainage persists at the abandoned Faro Mine, posing a significant impact to the downstream receiving environment. Effective remediation strategies for acid-generating waste rock rely on detailed physical and biogeochemical characterization in order to assess mechanisms controlling moisture and oxygen flux through waste materials. Reactive transport models use geochemical data from field samples to quantify the contaminant loading released to the environment under certain meteorological conditions. These models require a surface flux boundary condition in the form of net percolation to quantify the amount of meteoric moisture which interacts with and drives geochemical reactions within the wastewater piles. Gabriella's research focuses on using an established soil atmosphere model to assess net percolation for a range of climate scenarios. So please join me in welcoming Gabriella.
Thank you so much, Kevin, for the introduction. And thank you everybody for taking time out of your day to sit here and listen to my research results here. I'm just gonna go ahead and share my screen. And is everybody seeing it okay?
Yes.
That's good.
Perfect. Thank you. So today I'll be focusing on presenting some of the initial results for my current master's research, which is focused on analysis of surface infiltration through acid-generating waste rock at Faro Mine. And so just before I begin, I'd like to thank CERNAC and Terranet for funding this research project. And thank you to Parsons Construction for your help on site during my field investigation. And most importantly, thank you to University of Waterloo for all of your collaboration and help on this project. It's greatly appreciated. And so before I start, I would just like to acknowledge that currently here in Edmonton, we are located on Treaty 6 territory, home of the First Nations and Métis people. I would also like to acknowledge that my research was conducted on the land settled under the final agreements with the Selkirk First Nation and also land of the Kaska First Nations. And so before I start, I just wanted to give a little bit of background on Faro Mine for those who might not know or haven't been there yet. So Faro Mine is located 15 kilometers north of the town of Faro and approximately 200 kilometers north of Whitehorse in the Yukon. So at the peak of its time, Faro Mine Complex was one of the largest lead and zinc mining operations. But unfortunately in 1998, it was abandoned due to the bankruptcy of the Anvil Mining Corporation. And so as you can see here in this figure on the right, I'm just pointing to a feature here, which is currently known as the main waste rock dump on site. And so the east portion of this feature alone was constructed from 1972 to 1990. And the east portion alone accumulated 46.4 million tons of sulfide-bearing waste rock. So this is a significant amount of material, which is now left to remediation efforts. So unfortunately, when this ore body was formed, there was a high pyrite content associated with this ore body. And so ARD is currently one of the largest environmental threats to the downstream ecosystems, and remediation efforts are currently in the planning phase to prevent further ARD from perpetuating in these northern ecosystems over time. And so remediation of these waste rock piles has been assessed previously using reactive transport models. And so these tools help predict the leachate quality and quantity from porous media such as waste rock. So these models are extremely complicated systems. And as Kevin mentioned, they have to consider a lot of different factors such as geochemical, biological, and physical properties of the waste rock itself, which is a feat in itself. So my research project is part of a larger collaboration with the University of Waterloo to develop a reactive transport model that will assess remediation efforts that can be applied to the main waste rock dump. So this is a large effort that requires a great deal of collaboration between different disciplines in order to make this possible. And so my portion of this research project is tasked with determining the surface flux boundary condition for the overall reactive transport model without a cover scenario in the form of net percolation. So this is a key feature of the model because it will determine how much meteoric water comes into contact with the acid generating material over time. So that was the first objective listed here. But my second objective is to understand how different design parameters or physical and meteorological parameters affect the water balance and my final net percolation value over time. So in order to complete this task, I completed both field and laboratory investigations. I processed meteorological data, and I'm currently using all of these parameters in an established soil atmosphere model to determine the net percolation that results from these input parameters. So the first step in my research project was to complete my field investigation. So I was lucky enough to get to site in the fall of 2019. And my initial scope of work was to include 10 test pit locations, but due to equipment availability on site, I completed surface sampling to a depth of 25 centimeters at 3 test locations. And so these test locations were chosen to be located near previous investigation sites that were completed by University of Waterloo in 2017. So this included one near borehole 2, which I'll just highlight here, test pit 2, and I took an additional 3rd location between the 2 locations. And so sampling locations between or by these previous test locations was done so that I could compare results, my results to previous investigations, just as a quality control check, and just out of pure interest to see if there are any changes with depth. So in situ testing was the main focus of this field investigation, as the structure created in waste rock piles really influences how the flow of water occurs through these materials. And so Guelph permeameter tests were completed to measure the field saturated hydraulic conductivity, and the sand replacement method was used to measure in situ density. And finally, I measured 3 different jet fill tensiometers and monitored them over the duration of the field investigation to understand or measure in situ matrix suction. And so after that, I took additional laboratory samples for further analysis. And so once I completed the field investigations, I moved on to complete sieve, hydrometer, Atterberg limits, and specific gravity testing. So parameters derived from the grain size distribution seen in the figure here classifies the surface samples as poorly graded sands with silt and gravel. And so based on the amount of materials passing the 4.75 millimeter mark, this material was predicted to behave as a soil-like material. And so this is important because it indicates that the matrix materials will govern the flow of water in unsaturated conditions in situ. And so knowing this, it becomes necessary to measure the soil water characteristic curve, which shows you the relationship between the volumetric water content and the suction that occurs in these materials. So typically soil water characteristic curves are directly measured in a laboratory setting, but laboratory closures provided the opportunity for me to use numerical estimation methods to determine the soil water characteristic relationship based on previous laboratory analyses. So for this work, I used the Zapata 2000 method available in SV Flux, and I also used this software to determine the permeability function as well. And so in lieu of laboratory measurements of the saturated hydraulic conductivity for these materials, I actually anchored the permeability functions using field saturated hydraulic conductivities. And this might actually be a more representative measure of the degree of saturation that can be achieved in the field in comparison to lab measurements derived from laboratory settings of saturation. So knowing that the SWCC is approximated, I wanted to compare my estimated relationship to those that have actually been measured in the lab. And so as you can see in the figure on the right here, the red curve represents data obtained from University of Waterloo laboratory analyses, and the gray trend represents my estimated trend. And so the University of Waterloo sample was taken at a depth of 1.5 meters from a test pit excavation. And knowing that the University of Waterloo sample has 10% less fines than my surface samples, the increased air entry value of my trend and the shallower desaturation trend fit the expected behavior of a material with increased fines. So knowing this, I was comfortable going ahead using this estimation for my SWCC in further simulations. And so once I had completed the analysis of laboratory results, I started to look at the meteorological data that's needed to input into the soil atmosphere models. So daily and hourly precipitation records from 2011 to 2018 were available, and these were directly measured on the main dump itself, which were measured about 100 meters from our test locations. And so parameters such as wind speed, net radiation, relative humidity, and air temperature were available in hourly and daily records from 2017 to 2018. To ensure that the precipitation data was appropriate for my model, I performed a quality control analysis on the precipitation data. So after plotting the cumulative precipitation, both hourly and daily, I saw that there were periods of negative cumulative trends, which technically and theoretically shouldn't happen because your precipitation value should be greater than or equal to 0. So therefore I sifted through the hourly and daily data, and I indicated all of the points that were error readings or negative readings, as you can see in the figure to the left. And so what I did was I removed these readings from the data set and I replaced them with a 0 millimeter reading. And then I adjusted the annual cumulative precipitation readings accordingly to my adjustments. And then once I performed the quality control data on the precipitation readings, I wanted to verify that the remaining readings I had identified as valid were in fact valid. So I compared days with greater than 10 millimeters of precipitation to corresponding days at the Faro Airport and Grum meteorological stations. So these are located, the Faro Airport station is located about 15 kilometers south, and the Grum station is located about 10 kilometers northeast of our site. So when compared against each other, it was evident that although the precipitation readings obviously weren't exactly equal, they did reflect storm events moving through on the same days. So I was comfortable moving ahead with the precipitation data that we have here. So another component of the precipitation data that's important is the snow water equivalent. And so a tipping bucket gauge was used to measure precipitation and snow water equivalent, which isn't ideal to measure snow depth and snow density, which then is converted to snow water equivalent. So I decided to implement my own estimation of the snow water equivalent for my numerical model. So instead of using measurements from the tipping bucket data, I used snow survey reports and previous water balance analyses to make an estimation. And snow survey reports are conducted by the government of the Yukon throughout the territory at different locations. And so I tried to choose different locations that were the closest to our site, but also had an elevation that was as close as representative as my site is. Because with changing elevations, you can have different snowfall readings annually and during the season. So the table contains the survey results at the end of each indicated month, so at the end of March and April. And these were averaged over the years from 2017 to 2019 snow survey reports. And then my fourth source was a water balance report, which used an energy balance method with a prairie blowing snow module software that used site-specific meteorological measurements to estimate this snow water equivalent. So comparing the two sources, or all of the sources together, it seems that they were within reasonable agreement with each other, especially at the end of April. So what I did was I took the average of the 4 readings at the end of April, which was found to be 92 millimeters. And so the way I'm implementing this into my model is that I divided the total snow water equivalent over a 15-day infiltration period at a even hourly intensity that was applied to the precipitation data as a rainfall intensity. And so once I had all of my input parameters, I started to look at the numerical model. So currently I'm using SV flux, which is a multidimensional transient saturated unsaturated flow model. So it couples the physical principles of water flow through porous media with atmospheric moisture demands to calculate the water balance equation shown on this slide here. So the equation seems fairly arithmetically simple, where I have my unknown, which is my net percolation, and then we have the precipitation that's measured, but we don't know the runoff and the actual evaporation yet. Actual evaporation takes a lot of inputs, and it's fairly complicated to approximate. And runoff is very computationally demanding. So this is where SV flux comes into play to help me estimate the net percolation, because doing so by hand would be a very large feat. So the geometry I'm using in this model is relatively simple. It's a 1D column that represents the depth of material sampled, the 25 centimeters. And I applied a climate boundary to the surface, which is all the meteorological data I sifted through. And I applied a review boundary condition to the bottom of my model, which simulates an unknown output condition, because I don't know the rate at which water will be flowing out through the bottom of my column. As we know, the permeability changes with matrix suction. So depending on that, that parameter, the model will figure out how much water is percolating through the bottom. And so I'm using average geotechnical properties from each test location as my base case scenario, where the average field saturated hydraulic conductivity measured was between 17 centimeters and 30 centimeters in depth, in situ depth. So this was found to be 1.6 times 10 to the negative 6 meters per second. And then initial conditions for the model are taken from measured in situ matrix suction, which was approximately 42 kPa of matrix suction, and that'll be used as the base case of an initial condition. And so just to iterate certain assumptions that have been made, this model will not consider the effects of freeze thaw and vegetation on the water balance. So dates for the simulation in each meteorological scenarios that I'll cover a little bit later have been chosen so that both the air temperature and the soil temperature at the 25 centimeter depth are above 0 degrees. So that was confirmed with soil temperature measurements at the meteorological station. And so minimal vegetation was seen on the surface of the waste rock dump, and that vegetation that did exist had very little leaf area index. So it's expected that there would be insignificant impact to the water balance due to vegetation. And so just thinking about the bigger picture for this research project, it is beneficial to run multiple climate scenarios in order to provide a range of these boundary conditions so that they can test the rigor of their model and different outflows from the waste rock pile. So 3 climate scenarios have been chosen, which is a wet year, an average year, and then an extreme precipitation event. And so just as a note, as you can see in the figure here, data from June of 2017 was missing, so both meteorological and precipitation. So for the meteorological data, I replaced the June of 2017 with average monthly parameters taken from 2018 data. That was the closest I could get for an approximation. And for the precipitation, I knew the cumulative precipitation that happened in June. So I applied that as an even rainfall intensity over the entire month of June. And so knowing all of the model inputs and assumptions, now I can kind of go over the initial results of my analysis. So first I'll be talking about the extreme event. So this happened on August 24th of 2017, where 37.9 millimeters of precipitation fell over a 24-hour period. And this simulation was again run initially unsaturated to the field measurements. And the water balance resulted in 41% of the total event percolating through the material. And the reason I ran the model for 72 hours was to see if there would be any effect of evaporation, or to see if a decent amount of the stored water within the matrix would actually evaporate off, just as out of interest. And so one interesting thing to note here is that there was no runoff generated. So this made me kind of think about what would affect runoff and like the water balance in general. So what I wanted to do was to see the effect of the antecedent moisture content on the water balance. So what would the initial condition of the model do to affect the water balance? So in this next scenario, I ran the exact same model, but with the initial condition of minus 25 kPa. Ideally, I would be able to achieve a near zero kPa initial water pressure. But because these simulations are so computationally demanding, a solution past this initial condition wasn't possible, and it wouldn't converge in the software because there was such a large jump between the initial condition and the climate boundary. So this was as close as I could get for this scenario. And as you can see, sorry, excuse me, you can see that there was an increase in about 10% of percolation just by changing the antecedent moisture content. So although it might seem like a small number in this 1D column, if you multiply that percolation by how much area you have on the surface of this dump, it does become significant for ARD generation. And so again, in this scenario, no runoff was generated. And I more expect this because if you assume a unit gradient, my field saturated hydraulic conductivity is larger than the maximum rainfall intensity hourly that we see in this analysis. So theoretically, there shouldn't be any runoff when the system is saturated. So no runoff being generated was a little bit expected in this scenario. And so in addition to understanding the effect of antecedent moisture content, I wanted to run a sensitivity analysis to understand how meteorological parameters affect my water balance. And so looking at this tornado diagram, you can obviously see that the net radiation had the largest impact in this water balance. So this is extremely important going forward for further field investigations to properly measure and characterize the net radiation to make sure you're not over predicting or under predicting the net percolation just based on varying this parameter alone. So it's important to understand where your variation in results comes from. And so just another point, you can clearly see that the daily air temperature had the least effect on the net percolation that resulted in my analyses. And so these are just some initial conclusions from the extreme event. So no runoff was generated, which was expected in more saturated conditions. And so again, net radiation had the largest impact on the water balance. But my sensitivity analysis is not completely finished. I still need to quantify the effect of further unsaturated conditions if the model convergence will allow, and also look at how the field saturated hydraulic conductivity will affect the water balance, because that has been a large parameter in a lot of different water balance analyses. And so the next scenario I was able to run was the yearly analysis for 2018. So this was run using hourly precipitation data. And so the snow water equivalent was applied from May 9th to May 22nd. And this is ran as a base case scenario. So again, my initial conditions are unsaturated to field measurements. And so the initial results for this base case indicated that 23% of annual precipitation would result in net percolation, which is about 86 millimeters in total. So again, if you multiply that by the area that you have on the waste rock dump, that's a significant amount of percolation. And so again, in this situation, there was no runoff generated. But if you look at how much actual evaporation was estimated, that's a significant amount of evaporation contributing to the water balance. So it's just something to note looking at the runoff as well. And so you can also see distinct infiltration events that correspond to precipitation events, which I thought was interesting. So you can really see that the resolution of your precipitation data does matter. If you're doing a daily versus an hourly, you might not be able to capture larger infiltration events such as those that you see here, which is extremely important when you're looking at wetting fronts that generate ARD through waste rock piles. And so again, I wanted to kind of look at how the antecedent moisture content will affect this yearly water balance as well. And so this time I was able to get -3 kPa, which was nice as my initial pore water pressure. And so I didn't use 0 as my initial condition because it could introduce discontinuities in the model. So I decided to go near a lab saturated value and see what would happen in my water balance. So this indicated that going to an almost fully saturated system, an increase of about 5% of net percolation will occur. And so again, it might seem like a very small change, but in the context of the entire pile, it is pretty significant. So again, we do see that the antecedent moisture content does affect the net percolation. And again, here no runoff was generated, which was expected again, because I'm using the same field saturated hydraulic conductivity, which is not exceeded by the rainfall intensity I'm using here, assuming a unit gradient. And so these are just some initial conclusions from my overall analysis. So although my model is not predicting runoff for the average surface, there still exist heterogeneities on the surface of the waste rock dump that won't match my analysis. So as you can see here in this picture, this was taken while I was on site. And you can see that there was a ponding event, which is indicated by the silt and the volume change in the cracking. So you know that water was likely ponding here at this location. And so if you have topographic depressions, or if you have areas with increased fines that weren't captured in my sampling program, you could have ponding on the surface, which isn't captured by my analysis. As well, increased percolation can happen in preferential flow paths. So when we were completing the Guelph permeameter tests, there was one location where the flow rate increased dramatically, cut off dramatically, and then leveled off eventually. And it was pretty evident that it was finding a path that it would be easiest to flow around. So we do think that there are preferential flow paths under this surface that could potentially increase the amount of net percolation compared to the base case. So just due to the general heterogeneity of waste rock piles, it's likely that there will be localized variations in runoff or percolation compared to the overall analysis that I'm completing. So just to keep that in mind. And so my current focus is looking at completing more sensitivity analyses for both 2017 and 2018. I'd really like to understand how the field saturated hydraulic conductivity plays into account when taking a look at the water balance. And also I'm currently completing soil water characteristic curves to confirm the estimations that were made in SP Flux. So obviously if there's large changes compared to what I've input into my model, I'll take care of that and make sure that it's representative of the material, but that's my current focus. And so these are just the remaining questions that I'm left with. So how does the initial condition in a further unsaturated state affect the water balance? So decreasing the antecedent moisture content past what I measured, how would that affect it? How does the field saturated hydraulic conductivity affect my water balance? The same with the meteorological parameters. And because the rainfall intensity I have from field data, it doesn't exceed my field saturated hydraulic conductivity. How large of a storm event is needed to actually generate runoff or change the water balance significantly? So whether this is a 1 in 25 year storm, a 1 in 50 year storm, or a 1 in 100 year storm, how would those affect the water balance? And hopefully I can get that data from the Canadian government to see what they predict for climate change and how that will affect the water balance as well. So yeah, that's just a thank you. And if there's any questions, I'd love to talk to anybody who has any.
Thank you, Gabriella, for your great presentation. That's very interesting work, and thank you for the insights you share with us. Yes, we're waiting for the question come up. Please maybe just allow me to ask a question based on what I understood on this presentation. You said the preferential flow path is very important, and I think your current model is not predicting that, right? Would you be able to like modify your model so that you can have a more realistic prediction of preferential flow path?
Yeah, so I think that will happen when I assess the saturated hydraulic conductivity and how it varies my water balance. So if I increase my field saturated hydraulic conductivity by an order of magnitude or 2 orders of magnitude to represent a preferential flow path, how will that affect the water balance? So I think I might be able to capture the variation that may occur in those preferential flow paths through altering the field saturated hydraulic conductivity.
Okay. Thank you. Oh, actually, I have a question from Ivan Barco. The question is there any advanced evidence of permafrost on site? How might that affect things?
Yeah, so I think, I don't know if there's permafrost, but I do know that the soil temperatures do reach below 0, definitely in the winter months. So I'd have to go back and look at the data, but depending if the snow actually acts as an insulator or not, an insulative cover during the winter. But the negative temperatures for the soil would definitely affect the water balance. It's just in my scope, I'm not kind of looking at that, but it could, if there is frozen ground, it would decrease how much percolation happens at the beginning of that snow melt. So yeah, it would affect the water balance.
Great, thank you. So I haven't seen any more questions now.
Yeah, it's Ward Wilson here, if you can hear me.
Okay,
that was
go
a
ahead.
Great presentation, Gabriella. Really good job. And
thank you.
I think it was 27% net infiltration annual. I would agree. That's where I would expect it to be. And while this isn't a permafrost question pops up, it's a waste rock dump, which is free draining. So I don't expect that there would be any permafrost at depth. So it's the annual cycle that does it. So, but yeah, very, very good. And you're right, the variations and so forth. But I think you've got a very good handle on the surface here. Thanks, Gabriella.
Perfect. Thank you, Dr. Wilson.
All right. If there's no more question, I would like to conclude this seminar. And thank you again, Gabriella, for your presentation and spending time with us. And yes, I just hope everyone will have a great day. And with that, see you guys next week.
Thanks, Lang.